Okay, let me just review about yesterday's lecture. So we have discussed about capacitor, where inside the capacitor, yeah, the space between these plates, the parallel plates, we insert a material called dielectric, okay? And usually this dielectric constant K here, K usually is greater or equal 1, okay? So K equal 1 is vacuum, usually. So greater than 1 usually, the dielectric constant. So as you see from, for example, from this capacitance, yeah. So this should be, because K usually greater or equal 1, so epsilon is greater or equal epsilon 0, okay? So it should be, if we insert insulator material, it has the electric constants greater than 1, so it should be increase the capacitance. Okay, so we have also discussed about circuit, capacitor circuit, series, and also parallel circuit. Okay. Okay, so I want to discuss today, I think the last part of our section about capacitor, it's about energy. Energy stored in capacitor. Okay, as you know that we recall potential energy. Potential energy. Do you remember the formula of potential energy? Cyril Josia.
Yes, sir.
Yeah.
Potential energy is MGH, right? If
Potential
it's
energy, electric potential energy. Okay, let's say this electric. Electric.
Sir,
Yes.
is it K times Q1, Q2 per R?
Okay. In terms of potential, let's say du here. Okay. Let's say not u, maybe let's say dE equals to. Usually, if we have the source of potential, let's say V, and we get, for example, Q here. Okay, the potential energy usually Q times V. Okay, if this object somehow a continuous particle or continuous things, yeah. So we just replace this Q here by infinitesimal dQ. And so we replace this by this dQ. Okay. So the energy that is stored in capacitor, let's say E, dE is equal to this one. It's the same thing. dQ. Okay, usually this one should be integral dQ. Okay, so if you from the definition of capacitance is Q over V. Okay. Like, oh, okay. Because this little q, so this should be not capitals. Let's say this q here, little q. So we get that v here is q over c dq. If you integral like this, it should be, let's say, 0 from capital Q. This should be q squared over 2c. Okay. So let's say, take for example, take parallel plate. Okay, this C here, we take A over D. Selim, hello?
Yes, sir.
Can you ask Humam why he's late or he's having trouble with connection?
Okay, sir.
Okay, so in parallel plates, Q is equal to equals to sigma times A. Okay, and the electric field is sigma over epsilon 0. This should be Q over epsilon 0A. Okay. So if we replace this E here, Q squared over 2C. Okay. This should be E0, I'm sorry, E squared times E0 squared, over 2 epsilon 0 A over D. Okay, this should be epsilon 0 over 2 A squared times A times D. Okay. So,
Sir?
yes?
Sorry to interrupt. Humam said he lost his connection.
Okay. Okay, thank you. So, you see that, let me draw again the capacitors, this parallel plate capacitor. So, this is A here, capital A, and this is the width D, okay? So A times D is a volume of the capacitor, okay? So this should be equals to epsilon 0 over 2A squared times a volume of capacitor, okay? So this formula, epsilon 0 over 2 squared. So this volume, I divided this formula into volume. Okay. The volume. So the energy over a volume. This is defined as the energy density U per volume. Okay, we have this energy is proportional to the sorry, maybe, okay. Maybe I should say this is not E, sorry. But I'm afraid you are confusing with the electric field. Let's say this is U, capital U. This is capital U. Okay, so this is capital U. Okay, this capital U here. This is only U, little u. Is energy density. Per volume. So this formula, although I derive from parallel plates, capacitor, this form, epsilon 0/2 squared, holds in general, okay? So this formula holds in general. So for electrostatic, for every object, yeah, this formula holds. I mean, this formula is valid for every charge, yeah, for every shape, yeah, for every case. Okay. Is there any question? So if we put inside the electric material to this space with the electric constant K, for example, then the energy, the density, the energy density of the capacitor, we just replace it epsilon 0 by epsilon times A squared. Okay. Any question?
Sir, I don't quite understand why, if there's a K, we use just epsilon.
So, okay, usually epsilon, epsilon equals to K epsilon 0. You mean this one?
Yeah, sir. I mean, if there's a K, why we use just epsilon? Is it?
No, epsilon is the electric permittivity, the electric material permittivity. Epsilon 0 is vacuum permittivity. That is a different thing.
Okay.
So the relation is epsilon equals to K times epsilon 0, where K also is constant here. 1 times CE. CE is the electric susceptibility of material.
Oh, okay, okay, sir. Understand.
Yeah, okay. Anything else? Question before I proceed to new section about direct current? Okay, that's for electrostatic, yeah, properties of, yeah, we have discussed so far until this section is about electrostatic material, I mean electrostatic cores. Yeah. So next we will be discuss about the magnetostatic, yeah, also the direct current and magnetostatic. So we will continue, let's say, okay, I will use this board also. So the current DC direct. Sorry, DC, not DC Comics. That's different things. I don't know, DC. Do you know the word DC coming from DC Comics? You don't know, okay. Okay, so the current, so usually in general, the charge, for example, Q, usually it travels with velocity V in general, whether it's at rest, or travels through space. Okay, so the current, electric current is, let's say, capital I or little I also, okay. I, it's related to the change of charge, if there are so many charges here, over interval, time interval. So it should be related to somehow the Q and also velocity, something like that. Okay, the current, it's related to this one. Okay, so the definition, if we have, there are so many charge that travels through, let's say, through space, okay? So there will be a change here, the net of change of, so if they travel through times, they move into this one, for example. So this is usually Q. This then become, this is from 0 to little q. So initially we have capital Q at A, for example. Then they move. Let's say they have moved in the same velocity, the same speed, for example, to point B. Okay. Then it will be this, the number of charges here in B increase. Okay. And the number of this capital Q here will decrease. Okay. So there will be a net charge here. Okay, that travels from point A, for example, to point B, to B. Okay, so this average current, let's say is delta Q, delta Q over delta T, this average current. Okay, if we take the limit delta T to 0, for simultaneously, for very short time, delta Q over delta T is dQ over dt. Okay, so the units of the current, unit of current is ampere. By short, this is capital A, this is, we write in complete name, ampere. It's a French physicist or mathematician, as far as I know. And this equals to C over second. So this is column. This is second. Okay. Any question? Okay, let's continue. Okay, usually if we consider, the material that's very good for, well, to flow the current, the good material, or let's say transmitting current, usually conductor, as I said. Okay, the conductor, let's say if I draw this cylindrical cable. So the conductor, there is so-called there are so many of them. This is nearly free electrons. Why it is called nearly? Because they can move this electron, and let's say this is an atom. This is an atom. Okay, this is also an electron. This is an atom. It can move freely through these atoms. And because the electrons are identical into each other, we cannot distinguish which one belongs to which atom, something like that, okay? So they can move freely to every atom, okay, in the conductor. So this nearly free electron is used to transmit, let's say, the electric field. Electric field. So in the material, in conductors, these electrons, they are, let's say, because they are nearly free electron, they move, let's say, freely for every direction. It's random. They move randomly. Okay. And for example, if there is an atom, there will be repel, for example, this one, or they repel or collision. So electron will have a collision with atoms. Then they are scattered, scattered, repel, scatter something to this one or to this one, okay, repel, something like that, scatter. Okay. And when this velocity is around 10 to the 6 meter per second, this, what we call it, the velocity of the electron, this nearly free electron, okay, in the conductor, they move randomly, okay. So if we, let's say, this cable, we connect it to, let's say, to the voltage, a battery, Okay, this is plus minus. There will be a current here. So before the current, so there will be an electric field, yeah, which they are somehow, the flow of the electron is not really random, but becomes, what is it? It's like nearly parallel, yeah, to this electric field. So this external electric field, for example. Okay, the red one, this electron will move according to, well, let's say not, sorry, it's opposite, yeah, sorry, the opposite. Sorry, I forgot. It will be the opposite, yeah, sorry. It will be the opposite. So the electron moves in the opposite of electric field, yeah. Let's say this one, okay. In general, they are in the opposite. But we could make, let's say, an imagination, yeah. So this nearly electron moves, this nearly free electrons in the conductor moves in the opposite, yeah, nearly parallel, in the opposite, yeah, nearly the opposite of the direction of electric field. So we could imagine that if electron move that way, we could make, let's say, a particle, we call it A plus, move exactly, is nearly parallel to the electric field, okay? And this is also A plus, let's say, and this is A plus. So let's say A plus, somehow it's we call it a charge hole. So this is an electron. The red one is an electron. Electrons. So this is a positive charge hole. A positive charge hole. So a hole is something like imaginative particle. Imaginative particle. It means that if electrons move to the left, it is, we can say equivalently that the hole, the positive hole, moves to the right. Okay, so it means that, yeah, let's say if the hole move to the right with velocity v, for example, then the electron move in the opposite. The velocity is minus v, okay? So this is the direction of E, electric field. This E coming from the battery, okay? So the battery produced in the material, in the conductor, is external electric field that moves this charge hole, yeah, from left, from, let's say, from A to B. Okay. Any question? So this positive charge here will be the direction of the current, not the electron. Okay. Any question? Any question? No?
I don't think so.
Okay. Is it clear, yeah? So this is reality. This is reality. But this is imaginary, yeah? Imaginative particle. This is real particle electrons. This is imaginative particle. Okay. So if we, for example, again, a conductor, okay, there is a hole here, a plus, with the velocity Vd, yeah, Vd is called drift velocity. Okay. So it means that the drift velocity that which, well, let's say if the direction of E is left to the right, and then the drift velocity also to left to the right, okay? This Vd. Because somehow we make, yeah, the motion of the particle of the electrons is no longer moves randomly, but it moves nearly parallel to the direction. Oh, sorry, the electron nearly positive. The hole moves nearly parallel to the electric field. Okay. Okay, so in general, this dI here, wait, I forgot. The order of drift velocity, yeah, drift velocity. So the order of drift velocity, the magnitude is around, let's say 10 to the fourth, minus fourth, meter per second. Okay, it's very slow, okay, compared to the walking speed. So random velocity V is around 10 to the 6 meter per second. Okay, it's very fast. The drift velocity is 10 to the minus 4 or minus 5 meter per second. It's very slow, okay? So the infinitesimal current here, so somehow in this case we have this factor called G here. G is the current density. Okay, this should be equals to G dot dA. Somehow it's flux here, flux of the density, current density. Okay. Looks like flux. So I should be the integral G times dA. Okay.
Sorry, can I ask?
Yes.
Does it have to be perpendicular like flux?
Sorry. What?
Does it have to be perpendicular like flux?
Perpendicular. Good question. Usually we have a normal factor inside this one. Yeah, no, it's not really, it cannot be perpendicular, I think. Yeah, cannot, because it is different like flux. Flux, you can parallel, perpendicular, or in general, you can form angle. Yeah? But this one, usually they are parallel to this normal factor. Because we measure how many charts or these charts is these charts is form this current density. This current density, how many charts that flows through the area of this cup, for example, the cylinder cup. Yeah, so it should be parallel. Okay, should be parallel. Anything else? Perpendicular should be 0, I. I mean, perpendicular, something like this. Yeah. If this is area, surface, for example, a disk. This is, let's say, the normal factor of this disk, yeah. Perpendicular, the G, something like this, okay? So let's say, we call it the perpendicular current in this case is 0, okay? But this is only parallel case. But parallel case, we don't have, yeah, okay. We don't have, I mean, this current density doesn't pass through an area, So only moves on the surface, okay? Okay, this G here only parallel to the surface. So we cannot define the current in this case, only density current. Okay, anything else?
So density is
Current
depends
density.
on the area of the.
Yes, of course, depend on the area. Current density depends on how many charges. Current density and their velocity.
Oh, okay, okay.
Current also depends on G and A. Okay. Okay, so it should be somehow N, this normal factor is parallel to the G, okay? So in this case, we could define the current density. For in this case, we cannot, okay? So this G here, like I said, it depends on the charge, how many charges. So many charges, usually we have this E here, the charge of the hole, okay? And how many? This usually like capital N. Capital N is the number of charge, okay, the number of the hole. Then usually, well, it is difficult, very difficult to, in reality, to measure how many charges, okay? How many charges that flow through the conductor. So usually we only consider the density the density number of charge, okay? This, we call it this little n here. The density number of charge. Okay? And also this is V here, but V here is the drift, not the random velocity. So should be this is equal, not proportional. Okay. So in general, we have this G here. Is kept a little n, E, V, D. Okay. So in the conductor, this is special case here. We call it Ohm's law. He's a German physicist. Ohm's law states that, according to his experiment, that this current density is proportional to the E. Okay, to the E. E is the external field caused by this voltage source. So because this is proportional to the E, so it should be there is a constant here. This constant, we call it sigma. Sigma is the conductivity. Conductivity of material, of conductor, material conductor, conductivity. Okay. So sigma here is 1 over rho. Rho is resistivity. Okay. Somehow we have a greater conductivity if the resistivity is small. Okay. So insulator, rho is bigger. Okay. So the conductivity is becomes smaller. Okay. So if this is the case, then I equals G times A, and this is equal sigma A times A. Okay. So if we have, for example, this is A, and for example, this is D. Okay. This A here is V or delta V. Sorry. Delta V over D times A. Okay. So as you know that delta V here is D over sigma A times I. So this become rho D over A I. Okay, and this quantity called this R here. Sorry, this is resistivity. Yeah, this is R here. Rho D over A. This is, I think this is resistivity. Resistivity. The resistivity. Let me see the book first. This row here and sorry. This is resistance. I'm sorry. This is resistance. This is called resistance. resistance. Okay, so the Ohm's law said that is not the potential difference equals to I times R. Okay, so Ohm's law is this one, state that the current density is proportional to the E, where E is the external electric field. I think that's the lecture today. Any question?
Is there already module 3 for this chapter?
Not yet, module 3. Module 3, I will give you after, I think after Thursday. Yeah? You have to collect first your homework for module 2.
Okay. And for the faculty quiz, until what chapter is it?
Faculty quiz, you mean
KBF, Pak.
yeah, online quiz, you mean?
Yes.
Okay. Wait a second.